Hello and welcome. In this video, we are going to be looking at the calculations that go along with projectile motion. Now, I did a previous video that talked through the concepts of projectile motion. If you haven't seen that video, I highly recommend that you go back and watch it. I talk all about projectile motion and how it works, acceleration due to gravity, and two main points that are extremely important when we start looking at the calculations that go along with projectile motion. The first of those key points is that the time taken to reach the apex equals the time taken to return to the original height when you ignore air resistance, which means if I have something that is in projectile motion, I launch it at some angle, that it's going to travel along that trajectory to an apex, and then from the apex back to its original height. And the amount of time that it takes to reach that apex is the same amount of time it takes to go from the apex back down to the original height. If it ends at a higher height than what it was launched, it will take less time to go from apex to the landing point than what it took from original launch point to the apex. Conversely, if it lands at a point lower than the original launch point, then it will take a longer period of time to go from apex to the landing point. So we're going to be looking primarily at examples where we are launching it from one height and it's landing at that same height, but we can manipulate that and talk about where is it going to be within that trajectory at given points of time, how high it's going to go given a period of time, things of that nature. So in the long run, the fact that it lands at the same height at which it was launched may not be of extreme importance. But the other point that is of extreme importance is that for an object launched at some angle, the time taken to travel from that original height to the apex and back to the original height is always going to be equal to the amount of time that the object has to be able to travel in the horizontal axis. That is what ties the y component of projectile motion to the x component. Otherwise, the two components are completely separated from each other, and whatever's going on in the y-axis has zero effect on the x-axis. Likewise, anything going on in the x-axis has zero effect on anything going on in that y-axis. The only commonality between those two is the amount of time that's taken. And that's how we can use information from the y-axis to find out about things that are going on in the x-axis, or vice versa. It's through that commonality of time. So let's go on and take a look at a couple of examples of projectile motion problems. So in this first one, it says a fireman 50 meters away from a burning building directs a stream of water from a ground level fire hose at an angle of 30 degrees above the horizontal. If the speed of the stream as it leaves the hose is 40.0 meters per second, at what height will the stream of water strike the building? Okay, so as I always instruct my students, draw a diagram anytime you're given a word type of problem. So I've got my fireman, very badly drawn, but he is 50 meters away from some type of building. So this is my 50 meters. Directs a stream of water from a ground level fire hose. So for some reason that fire hose is sitting on the ground, but it directs it 30 degrees above that horizontal. I've got my 30 degrees, and it leaves that hose at 40.0 meters per second. At what height will that stream of water strike the building? So a very crude drawing, to be sure, but it hopefully will help solidify in your mind kind of what's going on. Once we've got this crude drawing, that's when we can go about drawing a much better depiction of this, where we're only looking at the object that we're really truly interested in, and we can clean this up. So I would now redraw this and say, okay, here's my point. It's going to travel 50 meters to some type of building, and it leaves at an angle of 30 degrees with the velocity of 40.0 meters per second. I want to know delta y. We are dealing with the y-axis, so everything's going to be delta y within our equations dealing with that. Anything along the horizontal would be delta x. And then I always list out the information I'm given. So I know the change in distance along that horizontal is 50 meters. I know that theta is 30 degrees. And I know that the velocity in the resultant is that 40.0 meters per second. And the reason that's important is, as I discussed in the previous video with projectile motion, this 40 meters per second, it's not 40 meters per second in the vertical and 40 meters per second in the horizontal, but that 40 meters per second gets divided up into two components. Part of that 40 meters per second is directed in the vertical. Another component of that 40 meters per second is in the horizontal. And when you look at the way that I've drawn this out, you can see that it forms a right triangle. So when I need to solve for my velocity in the y-axis, I'm going to do that in green, I'm going to need to use sine and cosine functions, one or the other. Same thing when I solve for my velocity in the x. I'm going to need to use either sine or cosine. So looking at this, that 40 being my hypotenuse, then my velocity in the x is the adjacent, which means my velocity in the y would be my opposite side. So if we look at sine and cosine functions, remember that sine of theta always equals opposite over hypotenuse. Sorry, that looks like a B there. Let me clean that up for y'all. And cosine of theta always equals adjacent over the hypotenuse. So when I solve for my velocity in the y, my hypotenuse is that 40 meters per second, and my velocity in the y is the opposite. So I can rewrite this equation, velocity in y over the velocity of the resultant. Likewise, for my velocity in the x, my adjacent over the velocity of the resultant. And rearranging, I can solve and say velocity in the x would equal cosine of theta times velocity of the resultant, and velocity in the y is sine of theta times the velocity in the resultant. And then we can work that math out. And if we do so, what we're going to end up getting, so therefore velocity in the y equals the sine of my angle of 30 degrees times the velocity of the resultant, which is 40.0 meters per second. And when I type that into my calculator, what I find is that my velocity in the y is 20.0 meters per second. When I solve for my velocity in the x, velocity in the x would equal cosine of 30 degrees times that same velocity in the resultant of 40 meters per second. And what I find is that my velocity in the x is 34.6 seconds. So I've got my two velocities. And now what I can do is start looking at kinematic equations and figuring out how can I use all of this information that I've been given and have so far calculated. Well, the first thing that I can think about is the idea that velocity is distance per time. So if velocity is distance per time, and I know how far that stream of water has to travel in the x-axis, then I can manipulate this equation to say, okay, velocity in the x will equal that distance in the x, so delta x, over an amount of time. I know my velocity in the x, we just calculated for it, and I know the distance that it has to cover, that 50 meters. So therefore, time is going to end up equaling the distance the water has to travel in the x divided by that velocity in the x. So whenever I substitute in the values, 50 meters divided by 34.6 seconds, what I find is that that stream of water will take 1.45 seconds to reach the building. So again, why is that important? Well, as I said at the opening of this video, the time in the x-axis is going to be equal to the time in the y-axis and vice versa. So if I now know that that stream of water takes 1.45 seconds to reach the building, that's also the same amount of time that it has to travel in the y-axis. So at this point, I can use the kinematic equation that says delta y, the change in the height, is going to equal the initial velocity in the y times time plus 1/2 at squared. That water in the y-axis is working against acceleration due to gravity, and we have to take it into account. That's why it's in this equation. I cannot go back to velocity as distance per time and rearrange for distance in the y, because if I took this equation and tried to apply it in the y-axis, it doesn't take into account acceleration due to gravity, slowing that water down to a velocity of 0 and then accelerating it back downwards. This equation, delta y equals v iy times t plus 1/2 at squared, takes into account that acceleration due to gravity. So now I can start substituting in. My velocity in the y is what we solved for previously. So that is my 20 meters per second. I know that it has 1.45 seconds in which to travel, plus, now in 1/2, and acceleration due to gravity is downwards. And this is another key point. This velocity of 20 meters per second, that's in the positive direction if we define upwards as positive, downwards as negative. But acceleration due to gravity is acting downwards, which means negative 9.8 meters per second squared for acceleration due to gravity. And gravity is going to have the exact same 1.45 seconds of time in which to act on that water. And when you plug all these values into your calculator, you should calculate 18.7 meters. So what that tells me, back up at my crude drawing, is that this water is going to leave that fire hose, travel the 50 meters in a time period of 1.45 seconds, and it's going to strike that building at that height of 18.7 meters from the ground. And that's what the question was initially asking. So again, in this problem, we're using the information given to us to try to figure out first and foremost how much time this overall process is going to take. Because again, once we know how long it's going to take to travel a certain distance in the x, we can apply that time to the y-axis. Conversely, if we are given information about the y-axis that would allow us to solve for time in the y-axis, we could then take that time in the y-axis and apply it to what's going on in the x-axis. And that is what is happening in this next equation, or this next problem. So let's take a look at this one. It says a playground is on a flat roof of a city school 6 meters above the street below. The vertical wall of the building is 7 meters high to form a 1 meter high railing around the playground. A ball has fallen to the street below, and a passerby returns it by launching it at an angle of 53 degrees above the horizontal to a point 24 meters from the base of the wall. The ball takes 2.20 seconds to reach the point vertically above the wall. So A, find the speed at which the ball was launched. So as always, let's start with a little diagram of this. So what I'm picturing is I've got my flat surface where it tells me the ball is launched from, and that's a distance of 24.0 meters. It tells me that the building itself is 6 meters, but then it has an additional 1 meter tall wall So 1.0 meters. So altogether, my delta y is 7.0 meters. Ball has fallen to the street, passed by returns by launching at an angle of 53 degrees above the horizontal. So that now tells me 53 degrees. And to cover that 24 meters, it takes 2.20 seconds. Okay. Now, don't get confused by the fact that it says to reach a point vertically above the wall, because really what that's telling you is this ball is launched, and after 2.2 seconds, that's when it's vertically above that wall. Okay. So that's how I'm able to take that 2.20 seconds and know that's how long it takes to travel the 24 meters. And right there in that, we should see a nice little kinematic equation where we know that velocity, again, is distance per time. Well, that distance, 24.0 meters, divided by the time that it takes to travel that 24 meters, 2.20 seconds. Sorry, wrong units on that. And when I calculate that out, I find that's traveling at 10.9 meters per second. But that is along the x-axis. So when I'm looking at this, I'm going to redraw it, an angle of 53 degrees, and I know that the velocity on the x is 10.9 meters per second. So what I'm trying to solve for is that hypotenuse, and I know that cosine of theta equals adjacent over hypotenuse, but that adjacent is my velocity in the x. So therefore, my hypotenuse, or the speed at which the ball is launched, is going to end up equaling the velocity in the x divided by cosine of theta. So 10.9 meters per second divided by the cosine of 53 degrees. And when you solve that out, you should find 18.1 meters per second. So now I know the speed at which it was launched. So that's part A. Part B asks to find the vertical distance by which the ball clears the wall. Okay, well, for that, we need to know the velocity of the in the y-axis. So velocity in the y, again, if we think about sine and cosine, that's going to end up being the sine of theta times the hypotenuse, which is what we just solved for in part A. So the velocity of y is going to be the sine of 53 degrees times the hypotenuse of 18.1 meters per second. And when you solve for that, that is 14.5 meters per second. Now that I know the velocity and I know the time that it's in flight, that 2.20 seconds, I can go back and use the exact same equation that we used in the previous problem, where we've got delta y, our change in y, equals our velocity in the y times time plus 1/2 at squared. So my velocity in the y is 14.5 meters per second. It's going to travel at that velocity for 2.20 seconds, except for the fact that acceleration due to gravity acting in the negative, so negative 9.8 meters per second squared, is going to bring it to rest at its apex and then accelerate it back downwards. And that acceleration due to gravity is also acting over 2.20 seconds squared. So whenever I solve all these in, what I get is that ball, after 2.2 seconds, traveling at 14.5 meters per second in the vertical, that is going to be its height when it reaches that wall. Well, if the height of the wall is 7 meters, then what I can do, say, all right, it's at 8.2 meters of height. It has to clear something that is 7 meters. So therefore, it's going to clear that wall by a distance of 1.2 meters. And that's my answer to part B. The last thing says, find the horizontal distance from the wall to the point on the roof where the ball lands. So now it wants to find out, okay, it travels, it gets above that wall after 2.5 seconds, it clears by 1.2 meters, and then it's going to fall. So how far beyond that wall does it land? And for that, what I can look at is it's going to land at a height of 6 meters. So delta y, again, is going to equal v naught y t plus 1/2 at squared. But now my change in y needs to be 6 meters. Velocity is still 14.5 meters per second. It's still going to travel for a certain amount of time. And that's what I'm having to solve for first. Plus 1/2 at squared, so negative 9.8 meters per second squared, times t squared. And the reason I'm solving for time is because on its way up and on its way down, if this is my 6 meters, it's going to reach that 6 meters twice. So I have to find out at what point in time it's going to be at the second height of 6 meters on the way back down. So when you do this, you might recognize that this is going to end up as a quadratic equation. When I rearrange things, I'm going to end up with 4.9 meters per second squared, all times t squared, minus 14.5 meters per second times t plus 6 meters. And if you plug that into the quadratic equation, you're going to get two values for time. Okay? And when you look at those two values of time, the larger value, which is 2.46 seconds, is going to be when it reaches 6 meters of height for the second time. Okay? The smaller value will be the time when it reaches 6 meters on the way up. The 2.46 seconds will be the time that it reaches 6 meters on the way back down. And now that I have that time, this is when I can now look at the equation that velocity is distance per time and rearrange it. So velocity is distance per time, or distance equals velocity times time. So if my velocity is that, I just went blank on me. My apologies, y'all. Where is it? Oh, that's why I'm thinking weird. Sorry. It blocked my mind for just a moment. So if I'm going at 10 meters per second, and that is my velocity along the x, because again, I'm looking at this distance, and I'm wanting to know how far it is. So this is velocity in the x, and that's where my mind went blank on me for just a moment, so my apologies. So my velocity in the x, when we go back up to it, was 10.9 meters per second. So distance in the x is my velocity in the x of 10.9 meters per second. And it travels at that velocity for 2.46 seconds total. So therefore, when I look at that value, and I calculate this 10.9 times 2.46, I get 26.8 meters. And knowing that that building was 24 meters away, I can subtract the distance to the building, and I get 2.8 meters beyond the railing. So that's how far beyond. So to kind of summarize this, what's going on again is we are first using information in the y-axis as far as at what 2 points in time will it be at 6 meters of height. Using the quadratic, we find on the way up, we get one value. On the way down, we get 2.46 seconds. So now we can take the velocity in the x and say over that 2.46 seconds at a velocity of 10.9 meters per second, how far would it have traveled? That's my 26.8 meters. If it sees the building at 24 meters, then that means it will go 2.8 meters beyond the edge of that building. And that's what part C was asking. So there's two problems on projectile motion. Hopefully everything made sense. If not, feel free to leave me a comment, ask any questions, and I'll get back to you on them. Also, don't forget to subscribe to this channel so you don't miss when I upload new videos. Additionally, if you have ideas for new videos, please leave those in the comments as well. Appreciate your time. Thanks. Take care.